Greetings everyone and welcome to Revolution of Reality. In my previous episode, I described the crisis that has brought progress in physics to a halt. The bottom line is that physics might have been on the wrong track all along. For example, the universe could be a hologram. This idea has been attracting a lot of interest and research over the last 25 years. It was Stephen Hawking's final theory before he passed away in 2018. So if we don't know whether the universe is what we generally think it is, or something completely different, that indicates a crisis of understanding in physics. In this episode, I'll describe how physicists can be highly successful at the same time as being completely baffled by the stuff we are made of. In school, we start arithmetic in the first grade with 1, 2, 3, and it gets increasingly complex from there. Similarly, we learn that the fundamental building blocks of physics are these three basic particles: electrons, protons, and neutrons, and it gets increasingly complex from there. And unless we go beyond school physics, this is the type of picture that stays with us for the rest of our lives. It's the picture that informs us of what we are and what we are capable of. Since the fundamental layer in this picture is so important to the understanding of all things physical, one might expect that it would be presented as realistically as possible, and yet it is not. Particles are presented as tiny solid balls, but when we look on Wikipedia, we see atoms depicted very differently. The electrons are depicted as a cloud. The nucleus, which is very tiny compared to the overall size of the atom, closely resembles the electron cloud. This model is known as the quantum model of the atom. The model taught in schools is called the planetary model. It was found to be flawed and was replaced almost 100 years ago by the quantum model.
It's a white lie that we tell our children because, we don't want to expose them to the difficult and horrible truth too early on. It makes it easier to learn.
Indeed, it would be difficult to teach the quantum model at school, since even physicists have yet to understand it. Ever since the arrival of the quantum model in the 1920s, physicists have been grappling with this question: what the heck is a particle? Astonishingly, particles seem to be non-real. So if everything is made of particles, then what the heck is reality? And now in the 2020s, these two questions remain as unanswered as ever. From a scientific point of view, this is clearly a critical issue, and the stakes are extremely high. If we're getting particles wrong, we could be getting everything wrong. In fact, it's this crisis of understanding regarding the fundamentals of physics that has driven physicists to propose increasingly far-fetched versions of the universe. But how could the universe be a hologram if our school education paints such a different picture? To answer that, let's take a look at the differences between school physics and modern physics. Generally speaking, we get the impression from school physics that particles are solid and real. Their behavior is simple and relatable, since it behaves like a miniature solar system. And of course we assume it's settled science, since it's the most basic level of physics. Modern physics, on the other hand, is the complete opposite. It's none of those things. There is nothing solid in a particle. Particles are waves, or excitations in quantum fields, as I discussed in episode 3. Particles appear to be different when observed from when they are not observed. By definition, this makes them non-real. I will elaborate on this shortly. Particle behavior is far from simple. It is strange and confusing, and unlike anything we are familiar with. As a result, there is no consensus on the nature of particles or reality. Physicists have coined a term for all this strange behavior: quantum weirdness. For example, quantum superposition, a seemingly impossible phenomenon in which particles appear to be in different exclusionary states at the same time, like a cat that is both dead and alive. And that is what this cloud is all about. It's all about particles seeming to be in many different places at the same time. To illustrate this, let's take a look at the simplest atom of all, the hydrogen atom, which in familiar school physics diagrams looks like this. It has one electron, one proton, and no neutrons. In modern physics, this single electron is depicted as a cloud, which represents the electron in countless different positions all at once. That seems impossible, but before I elaborate further, let's take a look at the reaction of some physicists to this and other types of quantum weirdness.
Coming up, the realm of tiny atoms and particles, the quantum realm. The laws here seem impossible.
Objects do things that seem crazy.
It's very mysterious why that is.
And that's just very strange, right?
Really peculiar. To understand how profoundly weird this is, so ludicrous, he called it spooky. Today's results are truly shocking.
Absurd, crazy, ridiculous, completely bizarre. It is impossible to even comprehend. Don't even ask me why. All we can say is that is apparently the way the world ticks.
These reactions seem to indicate a crisis of understanding, since they refer to the fundamental building blocks of everything in the universe. However, in physics, understanding is optional to success. Let's take a look at the example of gravity. Centuries ago, Isaac Newton came up with the law of gravity that we learn in school, and most of us probably assumed he understood gravity. But, as Newton himself said, the cause of gravity is what I do not pretend to know, and today it's still a mystery. Despite this lack of understanding, Newton's law has been enormously successful, and it's the predictive power of the mathematical formula that is able to make it successful. Predictive power means the formula can be used to make useful predictions by plugging values into the formula, like we do in school. For example, it can be used to predict the orbits of planets, or the forces on a rocket traveling to the moon. A similar situation applies to quantum mechanics, which we can think of as the scientific term for particle behavior. Even though quantum mechanics is not understood, Erwin Schrödinger came up with an equation in 1926 that has led to great predictive power and success over the past century. Let's once again listen to the reaction of physicists as they enthuse about this predictive success of quantum mechanics.
So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
These statements confirm once more that understanding is optional to success in physics. The laws, which are always mathematical in nature, have been successfully verified many times over, and yet they don't translate into any common sense explanation in the real world. In fact, one of the founders of quantum mechanics, Niels Bohr, famously said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." So then, what the heck is a particle according to modern physics? And the answer is, it's a mathematical construct based on mathematical laws. Any explanation beyond that is regarded as a matter of philosophy, at least until some new breakthrough discovery changes the game, which hasn't happened in almost 100 years of quantum mechanics. This is why we still don't understand the nature of reality, because our reality is formed in some shocking and perplexing way from particles that are not understood. So the mystery of reality goes hand in hand with the mystery of particles. Over the past century, there have been many interpretations of quantum mechanics, which you can think of as attempts to explain how particles form our reality. Wikipedia lists 15 influential interpretations. There are plenty of others that have been published, but these are the ones regarded as having made an impact. The Copenhagen Interpretation is the one that became mainstream after quantum mechanics was initially introduced in the 1920s. Very briefly, the Copenhagen Interpretation posits that a particle is in many positions at once, or in a superposition, until somebody or something interacts with it, at which point it will be found in one single position, like the traditional picture of particles. Since real objects can't be in many places at once, the particle is regarded as being non-real until it interacts with something. This interaction could involve looking, so you could say that the particle is real when looking and not real when not looking. And after 100 years of Copenhagen, physicists are still grappling with the following question: does anything exist when we're not looking? This question was highlighted by Albert Einstein, who had very strong objections to Copenhagen, and famously said, "I like to think the moon is there, even if I'm not looking at it." If you think this interpretation is far-fetched, then take a look at the next one, the many worlds interpretation. In this interpretation, the universe is continually splitting into countless parallel universes, which means that many copies of you are being made as we speak. So as we can see, each of these interpretations includes some inexplicable or far-fetched aspect that prevents it from gaining a strong following in the physics community. A now famous poll was conducted at a conference on quantum mechanics and the nature of reality in 2011. And among the questions asked was this one: what is your favorite interpretation of quantum mechanics? The response from the attendees, who were mainly physicists, showed a wide diversity of opinion. The Copenhagen interpretation came in at 42% and many worlds at 18%. But this represents a big downward trend for Copenhagen over a 40-year period, and an upward trend for many worlds. This graph reflects a branch of physics that is not understood, despite being highly successful in terms of its mathematical laws and the application of those laws in modern technology. Now compare this with the public perception of how the universe works, based on the white lie of school physics. We believe that we have been taught the simple fundamentals of physics, which we assume is correct and settled science. Meanwhile, the fundamentals of modern physics are in a crisis of understanding that has been going on for almost an entire century.
Quantum mechanics, for just coming up to a century now, seems to have got away scot-free without having a unique way of explaining what the heck is going on. I'm now of a generation where we've managed to finally, I think, break away from the old guard. The founding fathers, Niels Bohr and Werner Heisenberg and Pauli and Dirac, who all said, don't worry your pretty little heads about why it is all the way it is. If you are going to be worried, go off and become a philosopher. We are doing physics and quantum mechanics works. We now got to the stage of saying, actually, that's not enough.
This philosophical aspect of modern physics comes with an astonishing feature. It means we could have a complete revolution of reality without changing the laws of physics, only the interpretation of the laws. So sometime soon, physicists could hypothetically find evidence that the many worlds interpretation is correct, and they could announce a new consensus in which we all seem to exist in countless parallel universes. However, that wouldn't have much general impact as far as I can tell, but what could lead to a radical impact on society is if physicists found evidence that the universe is holographic, because that is a universe in which powers of the mind and life after death do have a plausible physical explanation. And I hope you will join me in the next video to find out more.